Well, good evening, everyone. I'm Charles Schultz, and this is the Randomizer. And tonight we have an interesting term. We're going to talk about hyperspace. Now, a lot of people associate hyperspace with science fiction, and true, it's usually used as a tool for traveling faster than light or reaching other dimensions or doing other fantastic things. But in reality, hyperspace does have applications, and we'll get into that in some detail very shortly. Um, I would like to encourage everybody to go to the Universe Science Center or SchultzLaboratories.com, become a member, sign up and support our efforts to develop our virtual world, which is a 3D educational environment. Walk around, explore our galleries and exhibits, interact with them, and if you are homeschooling or if you're just trying to learn some new subject yourself and you want a specific class or set of exhibits put in, contact us and we'll see what we can do to expand our facility to meet your needs. If you wish to teach somebody your skills, the things you've learned in your lifetime, you want to share with everybody, we can create a virtual classroom or some sort of gallery for you to put your works on display. So don't be shy, contact us, send us an email, send us a contact, or join us on the Randomizer 6 p.m. weekdays, Eastern Standard Time, and share your ideas with us there. Bring your questions and comments and ideas, and we'll post them live on the segment, and people all over the world can hear what you have on your mind. So tonight we're going to talk about higher dimensions, hyperspace. So how do we know any such thing exists? Well, a lot of times when we look at our world, we recognize three distinct dimensions, and those dimensions can be very easily described by using a number line. Now, in a pedestrian sense, we have names for each of these directions, such as forward and backward. That's one of the axes or directions. Right and left, that's another one of our dimensions or axes that we use, and up and down. Now, what's interesting is if we were to assign a number value to each of these directions, we could exactly specify where anything in the universe would be located. That's kind of a big concept and sort of a large claim to make. How do we know it's true? Well, if you imagine a number line running from right to left, and we called it the x-axis, that's pretty traditional. And so as the numbers start at 0 in the middle, they go positive in one direction and negative in the other direction. You can see that if everybody agreed on the location of that line, then I could say any number and it would correspond to a single location on that line. All well and good. And we call that right and left. And if we had a little more mathematical bent to our thinking, we might call it the x-axis, which is very common. For people who work with computer graphics and modeling, they usually refer to the x-axis as the right and left axis. Then if we assign another axis called the y-axis, and this is often the forward and backward direction, we can put a number line on that one also. Now, if you've ever used graph paper, you know that there's an X and a Y on the graph paper quite often, and it denotes exactly where you are located on that sheet of paper with two numbers called coordinates. So these coordinates will give you a place on the X number line and a place on the Y number line, and if you go to both of those points, you can nail one exact location on your graph paper. Easy enough. But how about three-dimensional space? Here's where we add a third axis, and that's a number line for the Z, the up and down. Fantastic. With three numbers all taken together, a set of coordinates, we can locate any point in space anywhere in the universe, as long as we all agree on where 0, 0, 0 is located, the home position, and as long as we agree on the scale of the numbers, whether they're light years or inches, and as long as we agree where plus and minus happen to fall on those axes. So we have to have some agreements, but once we do, we can nail down a position anywhere. Think about navigating on our planet, the Earth. So we have latitude and longitude, and we all agree on where the 0 line is and where the equator and where the poles are. Those are sort of, well, they're defined by the rotation of the planet. The north and south pole are points that we can all agree upon because our planet literally rotates on an invisible line through the axis of the planet. And also the equator, the equidistant point, from the North and South Pole is one single defined circle around the planet. So we can agree on those numbers pretty easily, and thus latitude and longitude systems were born. Now, navigation on a sphere is one thing, but navigation in free space is another. We have another set of numbers we use called declination and right ascension that allow us to locate any point in the sky. And as our planet moves around the sun, we see that our position in space changes quite commonly. The position changes with a 360-degree rotation around our sun called a year. In the beginning, people thought 360, this magical, easily divided number, was the number of days in the year, but they soon found out it wasn't an exact number. We actually have about 365.2422 days in a year. In other words, in 1 year, we go around the sun, there's a little gap, we have to cover another 6 hours or so, and that's why we have a leap year. Every 4 years, that adds up to an extra day. But how does this relate to hyperspace? Well, many years ago, there was a fellow who was named Edwin Abbott, and he was an English school headmaster, a schoolmaster as they call him, and he wrote a book about higher and lower geometries. And he had a visualized process that explained very easily higher and lower dimensions. He imagined a world he called Flatland, and this book, Flatland, that he published in 1884, detailed a story of how somebody from our dimension, the three-dimensional universe, was able to communicate with somebody who lived in a flat universe, nothing more than a sheet of graph paper, so to speak. Now, we can imagine any point on that graph paper, and we can imagine a universe having one less dimension than our own, and the citizens being flat, thinner than a sheet of paper, trapped in this two-dimensional reality, as opposed to our three-dimensional one. It's easy to see that if you were to reach into that universe, they would see only a slice of what we were presenting through that universe. And so your finger would appear to be a circle getting larger, and then a bumpy circular sort of feature as you plunge your finger in and pulled it out of their universe. And they wouldn't be able to explain where it came from or where it went. If you were to push a sphere through that universe, you would see a point and then a circle, and it would get larger until it reached the radius of the sphere, and as the sphere slid down through the rest of their dimension, it would collapse again to a point and vanish. Now, it's easy enough for us to visualize that, but what if we go the other way? 4 dimensions is very, very difficult for most people to visualize because we don't have any references in our own universe. We have those 3 dimensions we recognize, but here's a trick. Old film-style movies had numerous pictures, one after the other, on a thin strip of celluloid, a type of plastic. And they would show one picture after the other very rapidly. And the illusion is you would see animation. You would see frame by frame, very quickly displayed in sequence, a moving picture. Well, what if you imagine our whole 3-dimensional universe to be one snapshot? And then another snapshot. And if you were able to present these one after the other, you'd see a complete solid 3D world around you, changing as each frame was presented. For many physicists, the picture of the flow of time is very much like presenting one picture of our world followed by another, followed by another. So in a sense, you can see 4-dimensionally if you look at the change of time on our world. And many people consider time to be a 4th extra dimension, one extra dimension above the 3 that we can normally move about in. What's interesting is when we refer to hyperspace, we're not necessarily referring to a higher dimension, what we often think of as an entirely different universe of sorts, or an extra dimension to our universe. And it's a little difficult to explain, but in science fiction, particularly in Star Trek or Star Wars or any of these fictional worlds, they use the trick of hyperspace as a means of stepping outside of our space and moving faster than light and then stepping back in at some other location. And is that possible? It may be. We don't know enough yet to say for certain. But in order to make it work, you'd have to think of it as a device that could generate a pocket universe that had the right dimensions. If you could do that, create a little bubble universe around your ship, you could then somehow detach from our universe, move around outside of it, where the speed limit might not even exist, and then reattach somewhere else. To anybody inside our universe, you will simply have vanished here and then sometime later reappeared somewhere else. So there's a lot of thinking that's gone into how this might be possible, and some people are seriously researching the possibility of reaching another dimension that sidesteps our own. One way of visualizing it is think of our flatland universe, the one that Edwin Abbott wrote about, and all the people being as thin as decals stuck on this thin sheet of graph paper. Now imagine another whole sheet of paper directly above it, and somehow being able to step into that parallel sheet of paper. You would be in a different world entirely. One of the things you have to be cautious about if you're capable of stepping outside of our own universe into a hyperspace is that maybe the laws of physics are completely different or won't support the electrical force or gravitation or any of the things we can imagine. If that were true and you were to step into that universe, you would instantly dissolve into radiation and energy. There'd be nothing left of you. So stepping into another universe could be a very dangerous business. It could result in you simply ceasing to exist. So the thought of being able to carry your own set of physics with you, the rules of physics, makes a really attractive possible solution to the escape from our universe to another universe, a pocket universe. And some science fiction actually works on that premise. One of my favorite authors from years ago, who was a speculative thinker, and he would take terms in our possible science fiction worlds and see if it were real, what would the implications be for society? Now, good science fiction is based on taking a plausible premise, something we might not know how to do, but might be possible, and then injecting it into, or people into that world, and seeing what the implications would be. One of the implications for higher dimensions would be making teleportation effectively possible, being able to lift something up here, move it over there, and drop it back down. This is very much like moving something in the flatland universe, lifting it out and placing it somewhere else. We can generally understand that this might be applicable to our own universe, but there could be some really tricky consequences. What if you were to lift a solid object out of our universe and rotate it and put it back in? What would be the result? One of the possibilities is that all of the matter in that would literally become turned into antimatter. It would spin backwards and have the wrong rotation. It wouldn't have the different electric charge, perhaps. But what would happen if you put yourself back into the universe and you were a complete mirror image of yourself? At the very least, even if it didn't change what type of matter you were made of, it would change all of your molecules to mirror images. You'd be unable to eat any foods. You'd be unable to use many of the chemicals around you, and some things that are inimical would be toxic to you, and vice versa. An interesting thing about biochemistry is we understand what are known as mirrored molecules, or chiral molecules. Biochemistry has right-handed and left-handed copies of many molecules. We, as living organisms, are made out of left-handed amino acids and right-handed sugars. And so anything that's made of a left-handed sugar might taste right, but not be digestible. Some of the artificial sweeteners that are on the market are made in exactly this manner. They are mirror molecules of sugars that your body can taste and appreciate, but not process. They end up simply going through your system and being excreted. But if you, as a whole organism, were lifted out of our universe into hyperspace, turned over, and dropped back in, more than likely, everything in your body would become a mirror molecule, and you would not be able to survive for very long because there's not much for you to eat here. That's another thing. If you were to go to another world where all the biochemistry was backwards, even in this universe, you wouldn't have anything to eat. One of the interesting facts that you'll discover is some of the molecules in our spices are sometimes right or left-handed versions. Peppermint and caraway are the same molecule, but right-handed and left-handed versions. So your taste buds definitely can distinguish the differences. Well, hyperspace as a theoretical construct is an interesting place to think. And if you wonder if those extra dimensions actually exist, it turns out that the answer is yes, in some sense. If you've ever heard of 10-dimensional superstring theory, which was invented by Michio Kaku, the physicist, many years ago, you understand that the thinking is there are more dimensions to our universe, to our space-time, than we normally can perceive. As it turns out, 10 dimensions describes most of the effects of our universe. We may actually have 11 or 12 dimensions. There are mathematical reasons for 12 dimensions, which I won't go into at the moment. But consider this. The electromagnetic force has 2 extra dimensions in order for it to work. The weak nuclear force has 2 dimensions. The strong nuclear force has 3 dimensions in order for it to work. Well, boy, that's 7 extra dimensions right there on top of the 3-dimensional space-time we know. There's 10 dimensions right there. Gravitation appears to extend into another dimension. That's 11. Time itself, by many physicists, is considered to be a dimension. And if that were true, then time travel would be possible if you could lift yourself out of this now and go back to an earlier point in this super-dimensional universe that we exist in. This isn't known if it's true, but many people suspect that it is. And it's possible, if you could create a wormhole, that one end could be anchored in the present and the other end in the past or the future. So, extra dimensions, hyperspace, it's not complete unreality. There are some good theoretical bases for these ideas, and there are mathematical proofs that actually insist that there must be an infinite number of dimensions. So, we don't know where we stand in that, but our universe probably has anywhere from 10 to 12 dimensions involved in it just to make it work. And if you were to try and make one of these fictional faster-than-light hyperspace drives, it's probable that you'd have to generate a pocket universe that had up to 12 dimensions just to be able to keep your matter together so you didn't vanish in a flash the moment you turned on your lightspeed drive. Well, anyway, if anybody has any questions about higher dimensions or other universes, present them. The floor is open, and I'm here to answer those questions for you the best I can. Meanwhile, I'm going to encourage you to go to schultzlaboratories.com or universesciencecenter.com. Sign up as a member and support our growth and our development. Give us some hints about what you'd like to see. Share your ideas with us, and we'll see what we can do to bring them to virtual reality. And as I see no questions on the floor, I'm going to read my quote for the day. For God did not send his Son into our world to condemn the world, but that the world through him might be saved. And that's John 3:17. A lot of people never get that far. So I hope that you've enjoyed this presentation on hyperspace and the snazzy graphic that I have behind me right now. And think about it. Extra worlds, extra dimensions, other places you might be able to go. They could be very much pedestrian, mundane worlds. They could be very, very radically different. If you could step out of our universe, you might step into an utter vacuum and die from lack of air, or you might step into a world that doesn't support matter as we know it at all. So there are risks, very dangerous risks. I think this is where you want a drone and you send it through and see if it can come back successfully first. That would be the real way to explore hyperspace. Well, thank you for watching tonight's episode of the Randomizer and our concepts about hyperspace, and I hope you will join us again every weekday at 6 p.m. Eastern Standard Time to hear about another interesting and fascinating scientific concept drawn out of our hat. And everybody have a wonderful evening, and as usual, make the world a better place, and thank you. I'm Charles Schultz.